This is Dr. Beck. Welcome to another triple science chemistry video. I'm showing you the specification points for this video on the screen here. This is the second in a series of videos dealing with limiting reactants. So if you haven't seen the first one, please go back and look at that one. Here is the second one. As always, please make sure that you are in a position to learn and learn quietly. Turn your phone off. Please put it in a different room or turn it off. If you're using a web browser to see YouTube, make sure other tabs are closed, especially social media. And as always, if I ask you to do any of the tasks, you should actually do them. If I ask you questions, and for this pencil, as always, for this lesson, you will need a pen, perhaps a pencil for any notes, a calculator, an actual calculator, not your phone, and a copy of the periodic table. At the end of this video, there will be some homework which I will set you for next week. Okay, let's remind ourselves about this little creature here. This is a mole. This is our favorite science joke. It has no bearing on what I'm doing today. It's just the word that we use to express quantities of chemicals during a reaction. Okay, now we're going to have a bit of a practice with a past paper question about reacting masses. So let's have a look at that one. Here it is, a past paper question from a triple science higher paper. I'll give you about 5 minutes to do this. Note that it's worth 3 marks. Set your work out as we have shown in the past. And whenever you're ready to come back to the video, press play and resume. So for now, please pause and come back when you're ready. Okay, hopefully that was okay. It helps here by the fact that the equation is actually balanced for you. It often won't be, but here it is. You're asked to calculate the mass of product being produced. If we start with 2 grams of calcium oxide, notice we are not given the mass of water, we don't need it. We can actually work out what we need to work out just using the masses that we have been given. Okay, I'm going to show you the mark scheme. Let's get ready for that mark scheme. I have that purple pen ready. Okay, so the relative formula mass of calcium oxide using your periodic table is 56. And that for calcium hydroxide is 74, and therefore there is a 1-to-1 molar ratio here, and if we calculate the number of moles actually in that quantity of calcium oxide, we can then scale up to work out the mass of calcium hydroxide produced. In this case it is 2.6, and any answer within that range you can see would be acceptable. Where it says ECF, that means error carried forward towards the bottom of the screen. If you made a mistake earlier and you've followed through with the correct calculation thereafter, you will get credit for that. But hopefully none of you made any mistakes and you've got the correct answer of 2.6 to 1 decimal place. Okay, let's move on. Today then, this title and objective remains the same as in the previous lesson, in the previous video. Today we are going to look at the second part of that specification point I'm showing you on the screen. But today we are going to once again look at reacting masses and limiting reactants. So we're going to refresh our memory and learn how we can use reactant masses to decide which reactant limits the amount of product formed and which is in excess. And okay, lots of information there. If you want to take all that in, please press pause. But I'm just going to read through the important bit for today's lesson. Students should be able to explain the effect of a limiting quantity of a reactant on the amount of products it is possible to obtain in terms of either moles or grams. So today we're going to focus on when we're given the mass in grams. It's slightly more complicated, but not hugely more complicated than calculating things in relative to moles. Okay, so let's make a start with a worked example. So as we see here, sometimes you will only be provided with masses and you will need to calculate the moles by yourself. If you have 4.8 grams of magnesium ribbon reacting in a solution of dilute hydrochloric acid containing 7.3 grams of hydrogen chloride, which reactant is the limiting reactant? Now, in any GCSE questions, you will be given the relevant atomic mass or relative atomic mass values. You don't need to keep scrambling looking at your periodic table. That's just a bit of a waste of time. So you're given, as always, the relevant parts to this. So notice we are not given the quantities in moles. You are given the quantities in grams. But we know what we can do with moles, and we know what we can do with grams, and with the relative formula masses. We can work out the number of moles and then follow what we did in the previous video. So the first step is we are going to calculate the number of moles required, and actually the first step would be to balance the equation. So here is our balanced chemical equation for this. We are starting with solid magnesium. We are reacting it with a solution of hydrogen chloride in water, which we call hydrochloric acid. We are producing magnesium chloride and hydrogen. Now, we are only interested in the reactants in this question. That's what the question is about. So we don't need to worry about the products at all for this. Once again, we can use this equation, either of these equations. So we are going to calculate the number of moles of our reactants. We are already given the number of grams, 4.8 grams for magnesium and 7.3 grams of hydrogen chloride. So we'll use those numbers. First of all, we can see on the screen here the number of moles of magnesium in 4.8 grams of magnesium is 0.2 moles. The relative atomic mass of magnesium is 24. 4.8 divided by 24 is 0.2. For hydrogen chloride, it's a little bit more complicated because that is a molecule, so we work out the relative formula mass and we find that is 36.5. The mass in grams is 7.3, so we divide the mass by the relative formula mass, and we find that for this quantity, 7.3 grams, that is the equivalent of 0.2 moles. Notice, and a reminder, that we must make sure that we're expressing the mass in grams. That's our base unit for these calculations. Okay, let's move on with our solution. You start with 0.2 moles of magnesium and 0.2 moles of hydrogen chloride. Okay, let's have a look at our balanced equation. From the balanced equation, you see that 1 mole of magnesium will react with 2 moles of hydrogen chloride. Therefore, if we scale up and manipulate that ratio, 0.2 moles of magnesium would actually need to react with 0.4 moles of hydrogen chloride for a complete reaction. Okay, in this case, we haven't got 0.4 moles, we've got 0.2 moles. So this reaction would not be complete. The dilute hydrochloric acid is what we call the limiting reactant. There is not enough for this reaction to go to completion. It's half as much as we need. Therefore, we would say that hydrogen chloride or dilute hydrochloric acid is a limiting reactant, and therefore the other reactant, magnesium, is in excess. Okay, so that's a worked example. It's substantially the same. We've just got an extra step at the front where we are working the actual number of moles out from the given mass and from the relative formula or relative atomic masses. So there's just an extra step right at the beginning. Okay, I'm going to ask you to have a go, please, at this question. There are 3 parts to the question. I'm just going to read out the first part and then we can just skip through the rest of the instructions. So aluminium reacts with iron 3 oxide, and that's the formula there, to give iron, metal, and aluminium oxide, Al2O3. So part A is a balanced symbol equation. Part B, you need to work out which is the limiting reactant for those masses. And part C is then look at the reacting masses given the fact that we start with 32 grams of iron. Sorry, beg your pardon. Calculate the actual mass of iron that could be collected at the end of the experiment. Okay, so I'm going to give you, what's this, 1, 2, 7 marks. This could probably take us about 10 minutes, but whenever you're ready, come back to have a look at this. If at this point you're still a little bit confused as to how to do this, pause and rewind the video, or even look at the previous video. But for now, pause and then return when you're ready. Okay, welcome back. Hopefully you didn't find that too difficult. We're just going to go through the steps of the calculation now. I'm going to use my visualizer. This is probably as difficult as it gets for triple science chemistry, for quantitative chemistry. So I'm going to show you how we would work this out using my visualizer. Once again, I gave you the relative atomic masses for each, and this will allow us to proceed with this question. So I'm just going to flick onto my visualizer. We are given the chemical formulae for each of these compounds, but we're also told the other names of the reactants and products, which are elements. So here we have an unbalanced chemical equation. Iron oxide, iron 3 oxide, reacting with aluminium to produce iron and aluminium oxide. Now this balanced equation, this is an unbalanced equation. We're going to balance it. This isn't very difficult, but I'm just going to go through that process now. Fe2O3 plus 2 atoms of aluminium produce 2 Fe plus Al2O3. There we go. That's the first part of our question done. Here is our balanced symbol equation. Well done if you got that right. The next part is we're going to determine which is the limiting reactant and which is the reactant which is in excess. First step is always to calculate the MR or the AR for each of these things, and then we're going to work out the number of moles from the given masses. Okay, if we do the maths for this particular compound using the relative atomic masses for each of the elements there, we end up with a relative formula mass of 160. For aluminium, it is 27. That can be found easily on the periodic table, or I gave you anyway. For iron, 56. And for aluminium oxide, 102. Now, we're not actually interested in the products here. Okay, we're interested in these, so we'll focus now on these two over here. I'm just going to rub that out and write that up here. So now we're going to determine the number of moles. We were told there were 32 grams of iron oxide, and therefore we can work out the number of moles by doing this calculation, which gives us 0.2. For aluminium, we'll do a similar thing. We have 16.2 grams of aluminium, and we're going to divide that by the relative atomic mass of aluminium to find the number of moles. The number of moles then would be 0.6. Now, let's work out the ratio. How do we do that? We divide both of those numbers by the smaller of the two numbers. So 0.2 divided by 0.2 would give us an answer of 1. and 0.6 divided by 0.2 will give us an answer of 3. Now, if we see from our equation that 1 mole of iron oxide reacts with 2 moles of aluminium to produce these products in the ratio of 1 to 2. However, in our quantities, in the masses we were given, the ratio actually is 1 to 3. So they've actually got more aluminium than we need. We only needed a ratio of 2 here. We've actually got 3. So we've got more aluminium than this reaction would actually require. So we would say that aluminium is in excess. So therefore, iron, I'm going to move this up, oxide is the limiting reactant. Okay, once all the iron oxide had been used up, the reaction would stop, but there would still be some aluminium left over because the aluminium is in excess. Okay, that's part B. What I'm going to do now is go to part C. Let's just remind ourselves what the question said for part C. Calculate the maximum mass of iron that could be collected at the end of this experiment. The maximum mass of iron that could be collected at the end of this experiment. Okay, let's go back to the visualizer. I'm going to take it all the way back to this stage. Again, we're going to look at the number of moles. 32 divided by 160. The iron oxide is limiting, so that's why we've chosen that one. The iron oxide is limiting. Once it's all used up, there'll be no more reactant proceeding. So, as to remind ourselves, there would be 0.2 moles in 32 grams of iron oxide. Now, we need to consider the molar ratio. Now, this time we're looking at the molar ratio of iron oxide to iron. Okay, now in our equation, we can see that 1 mole of iron oxide would react with 2 moles of iron. So this ratio is actually 1 to 2. Okay, now so we just scale this up. We're going to multiply this by 2. So the number of moles we would produce of iron would be 0.4 moles. So 0.4 moles of iron would be produced. Now we need to work out the actual mass of iron that would be produced. So we'd use our equation. We would say the mass is the number of moles multiplied, in this case, by the relative atomic mass. So it's simply from my equation, from my calculation, 0.4 moles, and the relative atomic mass of iron is 56. Put those numbers into our calculator very carefully, and we then come up with an answer of 22.4. The unit, therefore, would be grams. So given these conditions, and we're starting with 32 grams of iron oxide, we would produce 22.4 grams of iron for this reaction. Good, well done if you got all that right. If you're getting that right, then we're going for that grade 7, that grade 8, and that grade 9 in triple chemistry. So well done if you have got that right. If you're still a little bit stuck, go back, listen to what I've been saying for the last 5 minutes, follow it through step by step, and refer back to your previous notes. For homework, These questions are all in your booklet, and again, I'm giving you the first two as a minimum expectation, 42 and 43. And for those who are more confident and are aiming for those very high grades, I'm going to ask you to complete the extension work, which is also question 44 and 45. So please, for the next time we meet, when we will go through the answers to these, question 42, 43 as a minimum expectation. And if you're feeling confident and want to challenge yourself further, question 44 and 45, including the challenges as well, please. Okay, today then we have just finished off this little section. This week we've been looking at reacting masses, to look at limiting reactants, and to look at chemicals which are in excess. Thank you very much for your attention today for this video. See you again next time.